So good morning, everyone. This is Lab 10, and this is going to be hosted by me, Divya, Harsha, and Sophia here. So the agenda for today is we're going to do a quick recap for RNN, GRU, LSTM, and some attention components. And then we'll do some coding to train a basic sequence-to-sequence model with attention on a dummy data set. And then we'll work through the checkpoints that we have, and then we can take some questions in the end if you guys have any doubts. Please, you can message us in the chat here or reply to the Piazza post if you have any questions. So this is the outline for today's notebooks. We have 5 checkpoints. We'll first work on the dataset creation and the pre-processing part, and then we'll move on to the dot attention and the decoder GRU classes. From there, we'll go to the sequence-to-sequence attention class. We'll complete the training loop and initialize the network, and then we'll finally complete the translation function for the inference. So we'll probably spend around like 20 minutes on the slides, and then we'll spend probably like 30 minutes doing the coding and the run through. And then we'll leave the rest of the time for any questions you might have. So just a quick recap on recurrent neural networks. So standard neural network models like MLPs and CNNs are not able to handle large sequences of data because MLPs and CNNs only accept a fixed size vector as input, and they produce a fixed size vector as output. The weights are updated independent of the order of the samples that they are processed in, which is why we have RNNs, which are typically used for time series or like modeling large sequences. They accept both. They accept sequences both in the input and the output, and they are capable of remembering the past information, which helps us model time series data and other large sequential data that we might have. There are different categories of sequential model. The first one is just like a basic MLP that takes a single input and a single output. We have one-to-many tasks as sequential output as well for image captioning tasks. And then we have many-to-one for sentiment analysis tasks where we have a sequence of inputs and we map it to a single output. And for mission translation, we have a sequential input and a sequential output, which is a many-to-many mapping. And video classification as well is like a synced, we coordinate the input sequences with the output sequences for a many-to-many sequential modeling. So the main problem with RNNs is when the input sequence is very large, the past data tends to get diminished as we move along. So there's a vanishing gradient problem where the contribution from the earlier steps becomes insignificant as we move the gradient along the last few layers. So for this problem, LSTM was suggested as a solution. LSTM is kind of an RNN where there's 3 gates, basically. There's a forget gate, an input gate, and an output gate. In the LSTM, each cell stores a value called a state for either long or short periods of time. In the 3 gates, the forget gate controls the extent to which a value remains in the cell. The input gate controls the extent to which a new value flows into the cell, and the output gate controls the extent to which a value in the cell is used to compute the output. So we can think of LSTM as like a clever note taker. It writes down important things through the input gate. It erases all the unneeded or the older information that's not required in the forget gate, and it reads out the notes that's needed using the output gate. We also have GRUs, which is a type of an RNN, and it's used for for when an LSTM is needed, but it has like less computation. There's fewer parameters than an LSTM because they lack the output gate is not used in a GRU cell. So when comparing RNNs with LSTMs and sequence-to-sequence models, RNNs are able to learn sequential patterns by passing the information in time, but they struggle to retain long-term dependencies. So when the size of the input sequence is too long, as we saw, there's a vanishing gradient problem. So they do not, they struggle to maintain the long-term dependencies within the sequences. While LSTMs are more computationally efficient, uh, which make them better than RNNs. They, they are learning what to remember, what to forget, and what to output. And then we have sequence to sequence models which compress the entire input sequence into a single fixed length vector before the decoding happens. But if the sequence is too long, there is a compression bottleneck. So the information is squeezed into one single vector, so it is inevitably lost. So for like longer and complex input sequences, we need a different mechanism, which is when we introduce the concept of attention. So this will be handed over by Shivash.
All right, hi everyone. So thanks, Divya, for that introduction. Um, cool. So where have we left off? We're currently at dealing with the sequence-to-sequence task, which is where you have a sequence of vector inputs, and you decode them. They're processed by an encoder, compressed into a single vector context vector, and then a decoder attends to that context vector and outputs another sequence, maybe for a different task. A popular example of a sequence-to-sequence task is neural machine translation. However, this begs the question, what makes a good context vector? In class, we've studied what makes a good encoder, what makes a good decoder, and Divya has covered some of that with modern architectures like LSTMs and GRUs. But now let's switch our attention to the context vector. So as you just saw, we have RNNs that then evolved to LSTMs and GRUs to solve various problems, like the vanishing gradient problem or controlling the flow of information throughout hidden states of these cells. A single green block that you see here is one cell of a network, either the encoder or decoder. Um, However, even though you see that the architecture does get progressively more and more complex, they ultimately, all, and even if you have a unidirectional or a bidirectional version of these, they're all unrolled in time. So even though they might look complex as a single cell, when you unroll them, that is expand them for all the time steps that you're going to process the input for, uh, it does end up looking something like this, which is extremely linear. And as Divya hinted, we have to figure out what the problem with this is. It's essentially that these are all sequential architectures that, when rolled out through time, don't have uh, or aren't attended to specifically by the decoder. So the embedding vector that represents the entire input context is diluted over time. So as we have been speaking about, is there a way the decoder can choose which hidden states are most important to it for whatever its task is? So that brings us on to today's task, which is the reverse copy task. The notebook that you guys must all have does not really load a data set today. However, we manually create one for this reverse copy task. It's a data set of input-output token sequence pairs, like you can see on the right here. And it's a synthetic task that's used to test sequence-to-sequence models quickly, and that's the reason we'll be using it today. So how do we have the decoder manually select, or rather automatically select, which input embeddings are important to it? So for that, we have attention. Initially, it was introduced by Bardano, but today we'll be studying Luong attention, which is a more generalized version of that and rather more simpler. So on the left here, we have the blue square or blue rectangles, which represent our encoders. And then we have the red rectangles, which represent our decoders. You can think of this as a two-layer GRU or a two-layer LSTM. In code, it's implemented with this line that you see here. Now, if we want every decoder cell to have some weight for any encoder hidden state, the architecture might look something like this on the right, where your decoder state, h of t, has a weight matrix, a of t, that's multiplied with every single one of the encoder hidden states, that then essentially performs an average, not average, a weighted sum of the encoder hidden states, which results in a context vector, which is what's finally used for the decoding step. If this diagram looks inundating, don't worry, we will break down all the equations. So let's talk in terms of math. We have the GRU encoder, which takes as an input S input timestamps or S input tokens. And then let h be the vector of encoder hidden states, which has one per source token. Then these form the memory that the decoder will attend to, as we spoke about having weighted sum of the encoder representations. Then, at every decoding step, the decoder generates a hidden state. This is now a function of y of t minus 1, which is the previous time step, then the decoder hidden state at the previous time step, and then c. These form the memory that the decoder tends to. So, how exactly do we compute this alignment score? It's rather similar to what you may have seen in class with respect to the cosine similarity. We simply perform a dot product between q of t, which is our query, and h of s, which is the encoder hidden state. In code, this is implemented as torch.bmm. You'll see this in the notebook as well. So this computes an alignment score which measures similarity between the decoder query and encoder state. Now, once we have a vector of alignment scores, what do we do with it? We simply apply the softmax function, which then converts all of these alignment scores into a probability. That's this operator here, and is also a to-do in your notebook. So after this step, we formulate a probability distribution across all encoder steps. Next, as I said, we have the context vector, which is a weighted average of all the encoder states. The weight here is the attention weight that we just computed in the previous slide. This is also a to-do in your notebook, and the result is that it's a weighted average of encoder states that's conditioned on the decoder's current focus. After that, we then combine this context vector with the current decoder hidden state, as you see here, and it's implemented in code with torch.cat. And in English, this essentially translates to the fact that the decoder integrates the added context with the input embedding to get the next hidden state. Again, this is all really important. You'll see this in your notebook. Finally, once we've computed the next hidden state, uh, we add a final linear layer, which is also implemented in the notebook, and follow that by a softmax to get the probability distribution of the next token. So this softmax is applied over the entire vocabulary of output tokens. You won't see this explicitly in code because it's all implicitly encoded in the nn.cross entropy loss, which performs a softmax, which takes in uh, input logits, or in our case, the decoder logits, applies a softmax, and then a cross entropy loss with whatever labels you give to it. So in sum, that is the attention architecture we will be coding up today. And you can already see, while this might not be the attention you're very familiar with, you can see parallels, or you can think of how this can generalize to a much broader scheme. So as I said, we did start with Bardano attention, which was invented all the way back in 2014. What we saw just now is Luong, sorry for the typo, attention, which was invented in 2015. But the attention we're all familiar with is the QKV attention, which is all a part of transformers, which is this diagram that you see here. Then in that paper, they also explored other concepts like multi-head attention, which is almost always used now whenever we talk about transformers. Almost no one uses single head attention. And there are also other variants depending on your task, which are known as self-attention and cross-attention. But they all build up on the key formulation that we saw today, which is essentially computing an alignment score and then taking a weighted average or choosing where to focus our attention on given input queries. So these are some of the sources for today. Specifically, the paper that we're looking at is effective approaches to attention-based neural machine translation. Cool. So we'll be taking questions after the notebook. Sorry, this slide should have come afterwards, but now I'm going to give it to Sophia, who will walk you through the notebook. But actually, before that, do we have any questions on Zoom? All right. Feel free to drop your questions in the chat, but for now, I'll hand it over to Sophia. Thank you.
Hi guys, can you hear me? So we're gonna walk over the coding part for this lab. Um, could anyone on Zoom confirm that the notebook is accessible? The notebook is on Piazza, the one that we have to post, and then there should be a link that connects to like notebook dot um, this file. Right, I didn't hear a response, but I'm gonna assume that this notebook is accessible. So the topics we're gonna cover today start with the attention mechanism, simple neural net, translation with GRUs, connection with LAS. So in this lab, we're gonna review how a basic sequence-to-sequence model works for machine translation. We're gonna implement a GRU-based encoder-decoder that includes the attention mechanism. We're gonna train the model on the small, which is a toy data set, like Sri Harsha mentioned, to demonstrate that the effect of of the attention mechanism. We're gonna discuss how this architecture ties into the LAS. So we will keep the data set small and like kind of artificially constructed so that the training can happen very quickly. We can look into the code and the concepts. However, the idea can easily be extended to a larger real world machine translation tasks. We're gonna have 5 breakpoints in this notebook. Please let us know if you have any questions with completing them, and feel free to either raise hand or comment, or just like send a message on Zoom once you're done with the checkpoint, so that we have a grasp of the time. All right, the first part that we're gonna look at is simply run this import and setup file. I'm sure up until this point of the semester, we have all been very familiar with the imports, setting seeds, checking which device you're on, hopefully. And I'm on CUDA, so which is good. The second part would be a quick recap. So the basic sequence-to-sequence without attention. Okay, a simple sequence-to-sequence model has a encoder and a decoder. The encoder pre-process the input sequences token by token. The final hidden state of this encoder is assumed to summarize the entire input sequence. Decoder would initialize the hidden state using the encoder's final hidden state. Then it generates the output sequence, token by token. Any questions with this part? Okay. The problem is placing all the input transfer information onto just the final hidden state is often insufficient for longer or more complex sequences. For hence, the attention would was introduced. The attention was introduced to allow the decoder to look back at all the encoder states, focusing on the most relevant parts of the decoding step. So that's why we have attention. With attention, the encoder would still produce a hidden state for each time step rather than just the final one. The decoder at each output time step combines its own hidden state with all the encoder hidden states, which are all weighted separately to produce a context vector. These weights, the attention or alignment, can shift from one part of the input sequence to another as needed. In the LS framework, the listener, which is the encoder, is often a pyramidal or stacked LSTM or GRU that encodes the input. In speech tasks, it's often frames. For attender, it computes a relevant score between the decoder state and all the encoder states. For speller, which is the decoder, it used the attention context and its own hidden states to generate the output, which is often one character or a subword at a time. We'll implement a simplified version here using GRUs for both the encoder and the decoder with a dot product attention mechanism. All right, let's do this. This is our first checkpoint. Please take a look at the first checkpoint that we have two to-dos here. We'll wait for, we'll wait for 5 to 10, we'll wait for less than 10 minutes for you to look over this part of the code and think about what to put into those to-do blocks, and we're gonna talk about the answers. You could also refer to the slides that Sriharsha just mentioned about reverse copy task. What exactly are they conceptually?
Can you hear me?
Yes.
I think we don't have access to the notebook. It just says access denied. So maybe we need to have the have the.
Yeah, we'll take a look.
And put the checkpoints in.
But that's an ideal guide, right? If you copy it to your own. Yeah, I'll do that right now.
Yeah, so it's the last one.
Yeah.
This is not here. You can just share this one. I want this. I have the. Yeah. Or we can just use the one.
Awesome. Um, we have just updated the access. Could if anyone could check on the Piazza post that and confirm with us that the current one is working, that'd be amazing. Okay, cool. Um, any idea on the first to do? What is what's the answer to the SOS index? So what does it represent here? Okay. Would anyone care to share what does this code, what does this block of code, like what is it doing here? What is a reverse copy task? Like what are we doing here? Okay, so in a reverse copy task, the model is given a random sequence of characters and is asked to output the reverse of the sequence. So this is a well-known synthetic task to test sequence-to-sequence models. And with a sufficiently large training set and a small model, training can be complete within just like a few minutes. So in this part of the code, the first step we do is to extend the vocabulary to include digits and then create the source vocabulary list, then special tokens, then all the lowercase letters, digits, and finally the space character. So this code automatically oh, there are two more to this. The number of training and number of tests. Cool, yeah. So this just creates a simple training data and then the raw index sequence for training and test. So this code automatically creates training data for a simple reverse string task. The idea is to teach a model to take a sequence of characters and output the same sequence backwards. It first defines the vocabulary with include lowercase letters, digits, spaces, and some special symbols, and then randomly generates strings that are made of letters, digits, and spaces. So for each string, it creates a training pair. The input is the original string, and the target output is the string reversed. Any questions with just like generating the data set? Should be pretty straightforward. All right, then let's take a look at the model architecture. So the first one is the encoder, which is a GRU. It embeds each source token into a continuous vector, processes the embedded sequence into a GRU, produces an output for each time step, not just at the final step. For the attention, so we're using dot product attention here. At each of the decoding step, we compute the attention scores between the decoder's current hidden state and all encoder hidden states. We then take a weighted sum of the encoder states using the normalized attention scores as weights. So we can look at some math here. This part is also referenced in the slides, so I'm gonna skip that. For the decoder, which is a GRU, at each decoding step, the decoder takes the previous target token and or the embedding plus the context vector from attention as an input, updates its hidden state through a GRU, and then predicts the next token with the linear and softmax layer. And then we will implement a single layer GRU for both the encoder and the decoder for simplicity. Here is our second checkpoint. Okay, how's everyone feeling about this part of the code? That's just three different parts. I think there are three to-dos in this section, in this checkpoint. So in the second checkpoint, this code builds the main parts of a model that learns to read a sequence and then writes another sequence. It's like reading a word and then writing it backwards. The encoder GRU takes the input, for example, a string of letters, turns each letter into a number, which is embedding, and then use the GRU to understand the whole sequence, saving important information in the hidden states. The dot attention parts helps the model focus on the most important parts of this input while generating the output. It checks how closely each part of the output matches what the decoder needs at the moment, given the higher weights to the most relevant ones. The decoder GRU then uses the previous output, the focus information, which is the context, and then what it already remembers to predict the next letter in the reverse sequence. In short, this code let the model read, remember, focus, and then write out the new sequence step by step. Any questions with any of the functions here? We're probably seeing very similar structures in the homeworks at this point. Okay, next part, we're going to talk about a full sequence-to-sequence model. Now we're combining the encoder GRU, dot attention, and decoder GRU into a single module that encodes the entire source sequence and iterate over the target sequence at each step. While during the iteration, it applies attention to get the context vector, feeds the previous token embedding and the context into the decoder GRU, and then predicts the next token distribution. Let's look at the third checkpoint if we don't have any questions here. So this code builds the sequence-to-sequence attention model, which connects the encoder, the decoder, and the attention parts to work together. When the model runs, the encoder reads the input sequence and turns it into a set of hidden states that represents meaning. And the final encoder hidden state is to use to start the decoder. Then, for each step in the target sequence, which is one of our to-dos, the model gives the decoder the real previous token instead of the one it predicted. The attention part looks at the encoder's outputs and figure out which part of the input are most important for the current step, creating a context vector and that summarizes that information. The decoder then takes the current token, the context vector, and its hidden state to predict the next token. This process repeats for every step, and all the predictions are stored and returned at the end. In short, this class defines how the encoder, attention, and decoder works together to return an input sequence into an output sequence, one token at a time. Any questions with the to-dos here? Then we'll do a simple training loop at our toy dataset. The steps are the first is the forward pass. We'll get the outputs of shape, and then compute loss versus the ground truth, and then back prop and update the weights. We'll do a teacher enforcing at 100% to keep it simpler just for demonstration. Here is our fourth checkpoint. Okay, any questions with this very simple training step? We just put the encoders, the dot attention, the decoder together, and then we have a sequence to sequence, and then there's an optimizer. There are a couple of to-dos there. We can train very fast. All right, so in this train model function, so after we run for 50 epochs, where like each epoch takes random batches of the input and the target sequences, feed them into the model, and then adjust the model's parameters to reduce prediction errors. The model receives the target sequence shifted by one token, so it learns to predict the next character at each step. The loss, which is the difference between predictions and the current outputs, is calculated using, I think we're using cross entropy here. And then the optimizer updates the model to improve the performance. I think we're using Atom. Some other common ones we have all seen them in the homeworks. The second part of the code initializes all the components, encoder, attention mechanism, and a decoder, then combines them into a sequence-to-sequence attention model, sets the Atom optimizer and the loss function, and finally calls the train model to train it for 50 epochs. Hopefully we can see that the accuracy is improving as the loss is dropping for just within 50 epochs. Any questions? All right, then let's talk about inferencing. So let's write a function to predict the translation, which in our toy case is a reverse string. We will encode the SRC, start the decoder with the SOS symbol, repeatedly computes the attention to context and a decode step to predict the next token, stop when we predict the end of sentence, or reach the max length. So this is our last checkpoint. There are a couple of to-dos. There are 4 to-dos here. Okay, are we good on time for this part? The last checkpoint? Okay, so this code defines and tests an inference function for the trained sequence-to-sequence model. In this case, to see if the model can correctly reverse the strings that it hasn't seen before. The translate function takes a text input and runs the model step by step to generate the output sequence. It first converts the input text into numeric indices, pass it through the encoder to get hidden representations, and then initialize the decoder using an encoder's final hidden state. It then starts decoding with the start of sequence token and then use the attention mechanism at each step to focus on the most relevant part of the input. The decoder predicts one token at a time until it outputs the end of sequence token and then reach the maximum or it reach the maximum length. So each predicted token is converted back to the text at the end. Here we can see that when the input is getting too long, it's not working correctly. Okay, any questions? All right, the last part would be discussion and connection to LAS. Attention helps the decoder focus on the relevant parts of the input at each output step rather than relying solely on the encoder's final state. The listen, attend, and spell is a speech recognition system that similarly listens, which is encoded the audio frames into hidden representations, often with a paramedical encoder for length reduction, and it attends to use the attention mechanism, for example, dot product or location based, to combine the decoder state and encoder outputs. And the last step, it spells, which is decodes one character at a time using LSTM or GRU based decoder. So the key takeaways for this part of the coding exercise is the attention mechanism would drastically improve the ability to handle long sequences. The same principle, attend to relevant encoder positions for each output token, drives many modern architectures, including the transformer, which is multi-head self-attention. In LAS for speech, the idea is identical, just with more specialized encoders and often the character level or subword level decoder. Okay, this is all we have for the lab. We're gonna stay for another 5 to 10 minutes for any questions. Other than that, please enjoy your weekend.